All right, we're back. We're still on page 6 of note 16. We're doing first derivative, second derivative of parametric equations. And let's dive in. So I'm going to do this. I'll probably check it on the calculator. Let's say, so we want the first and second derivatives as a function of t and at t equals 4. And find the equation of the tangent line at that point. All right. So we're going to find dy dt. We're going to find dx dt. And then we'll combine those to find dy dx. So dy dt is going to be 2t over t squared minus 9. Dx dt is going to be 2t over t squared minus 3. That's kind of interesting. So then in combination, dy dx is going to be, so you get 2t over t squared minus 9 over 2t over t cubed minus 3. Multiply by the reciprocal, the 2 t's cancel, and we get t squared minus 3 over t squared minus 9. It's only defined for t greater than 3, which is good because I don't want to mess with that domain. So t is greater than 3. All right, given, nice. Now to find the second derivative. So we want the second derivative. That's going to be the derivative with respect to t of dy dx, which is, I guess I'll use the quotient rule. You can use a +6 -6 trick on that. Actually, maybe I'll do that just so you can see it. So what I'm going to do is I'm going to add and subtract 6 in the numerator here. So I'm basically doing +6 -6. And then, so that's nothing, right? But then I get t squared minus 9 plus 6 over t squared minus 9. And I can rewrite that as, so t squared minus 9 is just 1. T squared minus 9 over t squared minus 9 is 1. And then I have plus 6 over t squared minus 9, but I can write that as 6t squared minus 9 to the -1. The reason I would want to do that is to avoid using the quotient rule. Now I can just chain rule this thing. So it's -12t and then t squared minus 9 to the -2nd. So I brought the -1 down, multiply by 2t, that's -12t, and then subtract 1. And then over dx dt is 2t over t squared minus 3. Like that. So this like cleans up to what though? So 2t and -12t just give you -6. This guy goes to the numerator, and then this will be in the denominator, I think. All right, I think that those are my first derivative and my second derivative. So I'd probably write that one without the +6 -6 for sure. And then this, the second derivative, is this, I think. And then what are we doing? We need to find each of those at t equals 4. Okay, so dy dx such that t equals 4. Remember, dy dx is a function of t. So that 16 minus 3 is 13 over 16 minus 9 is 7. Second derivative. I mean, this is just substituting, so I don't know, not that exciting. This is -6 times 13, great. And then over, because I'm plugging in 4, 16, so 7 squared is -60, -78 over 49. Interesting. But that's concavity. And like all you ever really care about is the sign of concavity, so like not really a big deal. And then we want the tangent line. So x of 4 comma y of 4 is going to be the natural log of 7, the natural log of 13, natural log of 7. Gross tangent line. Natural log of 7. All right, so then our tangent line. Nice of this question to pack in like 67 parts. Slope that we got was 13 over 7. I hope that's right. I mean, I hope everything is right, you know? Ew, that's not right. X minus ln ln natural log of that. Golly, that was like a lot of doing here. So, ooh, you're not a highlighter. This was something we were asked for. This was something that we were asked for. And then our tangent line is something we were asked for. Gosh. There were like there were at least 5 questions in here, maybe more. Should we check it on the calculator? I guess so. Also, the next question is calculator, right? Write the equation of lines tangent to the parametrically defined curve at the point 0,9. So we can use a calculator. Let me just set up what I'm going to do here. So first, I need to figure out what value or values of t put me at 0,9. So x of t equals 0 means that 3 t minus 2 minus 2. You know what? I'm going to use a calculator. So that's going to give me a couple t values. And then y of t equal to 9 is going to give me a couple of t values. And then I need like mutual values. So I need values that make both of them true at the same time. And then we're going to find the tangent lines. So let's go to the calculator, get this done. All right, so I think that I'm checking the first problem that we did in this video first. So natural log of t squared minus 3, y of t, natural log of t squared minus 9. And then, all right, so the first derivative. This is the moment, right? So we either get this or we don't. First derivative, t squared minus 3 over t squared minus 9. Excellent. And then the second derivative is the derivative. Actually, I can just go up and I should be able to go up and steal this too. Here, but I need to change this to, actually, if I change it to this, I don't know if this pasting is going to work. Yes. This should like generically work now for a second derivative. And we get -6 t squared minus 3 over 2. Yay. All right. And then I was supposed to do this such that t equals 4. I was supposed to do this such that t equals 4. Things are looking good. And then I was supposed to do, well, just like x of 4, y of 4. And so I'm pretty confident we got that right. So we did it. Nice. All right. I'm going to update my x of t and y of t. That's the biggest mistake people make when they're using the calculator is they forget that. Like, calculator doesn't know what function you want it to use. It just does what you tell it to do. So if you don't redefine your x of t and y of t, you're getting the wrong answers and it's your fault. It's not your calculator's fault. Almost nothing's your calculator's fault because it doesn't think. All right, I need to figure out. So I'm going to do menu 3.1. Or I guess I could do, well, all right, I want to do menu 3.1 because this is how I always do it. X of t equals 0 for t. And so you get those. That's not super great. Then I want to solve y of t equals 9 for t. Oh, that's interesting. So it's the 2 weird ones that showed up twice. And then 2 is just a time when x is equal to 0. But when x is equal to 0, y is not equal to 9. So there are 3 times that x is equal to 0. 2 of those times, y is equal to 9. 1 of those times, it is not. So the values that I want are these weird, they came from the quadratic formula for sure. I'm going to store them. T1, I'll store as this. T2, I'm going to store as the other one. It's kind of weird. When you store a value, it doesn't say done. It repeats the value, but it's stored. When you store a function, it says done. It doesn't repeat the function, which is a little, is that inconsistent? I feel like it is. So I should be writing some of this, I guess. So I'm going to write down the values that made x of t equals 0. So that was 2 plus or minus radical 3 and 2. And then the values that made y equal 9 were 2 plus or minus radical 3. Therefore, the values that we want are t equals 2 plus or minus radical 3. I don't generally like writing plus or minus in my solutions because I feel like it's not really enough information. Like it is and it isn't. So now let's write our tangent lines. So I need to find dy dx. So I'm just gonna like scroll back up until I get to where I found dy dx. Here we go. So since I've updated my functions, this will give me dy dx. I get this. Ooh. All right, so I'm gonna do this such that t equals t1, and it'll be the slope at t1, which is 2 minus radical 3. So I gotta keep track of that. So let me just put my tangent lines. So we're using the calculator, so I'm just gonna like write them, I guess. I have 2 minus radical 3, comma, radical 3. And then the slope at that point. Oh no, that is the slope. So I don't actually know the y value yet. The y value I think is gonna be ugly. Dy dx is radical 3. Okay, so the y value, I need to do y of t1. Oh, I don't know the x value either. I'm making the classic mistake. Holy cow. Wait, hold on. My thinking is off. I knew the ordered pairs to begin with. That was given, right? So, I'm glad you're not seeing my work. So at t equals 2 minus radical 3, our tangent line is going to be y minus 9 equals radical 3 x minus 0. And then at t equals 2 plus radical, I'm just like shaking my head at my my work here. I bet it's the negative. Like, I don't know, but I think it's probably that. Change that to a 2. It is negative radical. You get that a lot of symmetry. All right, let's see what this looks like. So I'm gonna go to, I'm gonna add a graph page. And then I'm gonna switch to parametric. So menu 3 and then option 4. And I'm just gonna graph x of t and y of t. And like, I don't know what makes sense for t. Let's go negative 10 to 10. See a bunch of this if we can. And let me zoom out because I'm not really seeing anything interesting. Zoom out. Okay, all right. I think these are called like foliums. Like there's a famous, like the folium of Descartes, I believe. Now I'm gonna switch back to function mode. So menu 3.1, and I'm gonna graph 9 plus the square root of 3 times x. It's like really a bad idea to store x as a function because like it's gonna work, but like it feels like it shouldn't. Okay, and then 9 minus the square root of 3 times x. And we get this, and there you go. So you can see that. You can definitely see there's another time at which x is equal to 0, but at that time, y it looks like is also equal to 0. So not another place where you're at the point 0.9. And that's it. So I'm gonna go back to the notes so you can see the work that I did. There was a lot of editing in between you seeing it previously and you seeing it now, but you know what? It ended up looking good. So there we go. That's all we have to do. So I'm gonna end the video here. Be back in the next one to do some more, and I will see you there.